Now, let's say that there are a lot of games that we can convert to NIM and then solve. So let's start with one of them. So, you know, an easy problem in which you have a token on a tree and you can move it to one of its children each time and you lose when you can't move, like the token is on some leaf, right? This is like very easy game. Like I think everyone knows the solution for this problem. But yeah, let's give you some like let's say 2-3 minutes to think on this problem. So I repeat the problem. There's a tree and there is a token on the root. It's a two-player game. In each turn, the player moves the token into one of its direct children. And somebody that can't move, he'll lose. So you need to determine the winner. So yeah, let's have 2-3 minutes to think on this problem, which is actually easy. Okay, so easily they are loose states, and the state which is connected to at least one loose is win, like this, and like this is win too. And the state that has like all wins is lose. For example, if it was like this was lose. Okay, this is easy. But what happens if there are several trees and we are playing on like all of them, and in each turn we can choose a tree and move the token to next to some next children. Okay, like let's say we have this tree and also this tree. Now who wins? So we have several trees. Then uh, then now we at each turn it's like NIM. At each turn there we choose a set and move in there, right? Here we choose a tree and make a move there. But the difference is in the set we had some moves like removing 1, 2, 3, 4 or more like number of tokens, and here our choose is moving token to some children. Now how we can solve this? Like for, just consider these two, who wins? Just these two trees, who wins? Second player will win. Like with every tree, if we have some trees like two trees, both having height 1, always second player wins. Repeat the example. Last problem. Last line. Okay. So for every game, these two trees, and both having height 1, second player will win. That was just an example. Nothing that important. Just an example. Now try with different trees. Then let's more number of trees instead of 2. Like let's try for 3 and so on. Uh, try to somehow convert a tree to a set of tokens in the NIM game. It's not, maybe at the beginning it's not that easy, but let's see. So this, like a single node, is like an empty set. Why? Because you can't do any move here, you can't do any move here, right? Let's see what is this one. This is a set with just one token in it. You have one choice here, you have one choice here. But let's see what this looks like. Like if I want to convert this to a tree, how it will be. So I should have a node. I should have a node with two children, right? Because how many options do I have here? Two. To pick one token or to pick two tokens, right? I have two options. So root should have two children, okay? Then if I pick two, that's it. Like it should be like a single node. So this child shouldn't have any childs. But consider I just remove one of them, one other remains. So how many children should I connect to this node? Okay. Now let me know how this one should look like.
Either you can take all three, or you can take two, or you can take one. If you take two, then again this three.
If I take,
If you do the two one option, then this is the same tree which is a subtree of this option.
can you draw it on a paper? Show me. Like
This is the tree that you have created, right? This is already showing the state of two points, let's say 2 points.
yes.
What you can do is add one parent and two again. Add one parent and two. Like
Add one parent and then what?
two nodes below that. So that children.
Okay.
So like moving on those two children is equivalent to moving.
No.
Just one children.
Two children is right. No. Look, you have three options, right? So we should have three children. And this one is correct. And this one is correct too. But this one needs to add some children. Yeah, one children. So for this set, the equivalent tree is this. So it looks like, let's say, this tree is F3. So for making Fn, it's easy. Put a node, connect it to F0, which is a single node, then F1 and to Fn minus 1. And but you know, the thing is, we need to do the vice versa thing. Like now we can convert some set into some tree, but what we need is the vice versa case. We need to convert some some tree into some set, which is maybe harder. But let's start from somewhere. Like what about this? So which set it's representing? How many tokens I should put here? One. Like what about this? Yeah. Now try for this. Uh, were you be able to map this tree to a set of tokens? This tree. Yeah, empty. Because actually you don't have any, like, empty. Because actually you don't have any choice. Like you have some choices, but all of them are loose. Like you'll lose finally. So they are not real choices. So what about this one? What about this one? This is not for sure an empty pile because we have option to move here. So at least one choice. So it will have at least one token, but maybe more. Why three? Because it has three children? No, like this tree has four children, but it's just like one token. Four? No, it can't be for sure four. Like for four, you should have four choices, but we have at most three. So possible game path? Last four moves? What do you mean by last four moves? So these children is like an empty pile, right? These children is like pile with just one token. Let's see what is this. So for finding this, we need to find these two. This is empty, and this is a pile with two, right? Then you need to find how many, like, what represents this. you need to find. And then after that, you can find answer for the root. So to magnify, this one is consider a name game. In some turn, you are forced to use some specific pile. Like you are forced. Like you can't choose on others. You are forced to use this one. Like let's say this pile has 10 tokens. Do you prefer this pile to have 10 tokens or 20? Like if you can choose, like you're forced to choose a pile, you don't know how much tokens are in it. What do you prefer? You prefer that this one has 10 tokens or 20? 20. More tokens, more options. Maybe I can win. Like everything you can make with this, you can make with this, right? So now let's try to find the like let's use the word that I try to avoid using for like 1.5 hours, which is Grundy number. So I usually reveal the topic name at the end. So yeah, we are close to the end. So I can now reveal it. Like Grundy number. Let's say Grundy number of each vertex shows the number of tokens in the pile respective to subtree of that node. So Grundy number of this node is 0. This is 0. This is 1. 0, 0, 0, 0, 1. Then 0, 1, 0, 2. 0, 1, 0, and this is 3, right? Because we said that f of this is this. So root of this, Grundy number of this is 3. So this is a complicated tree. So like for this, it's obvious, right? So we had no challenge. This is 0, all we know. This is 0, this is 1. And here you have two choices, 0, 1, and it's 2. Great. And this one, you have 3, like you have 0, you have 1, you have 2, so this is 3. But this is different. Let's see. So 0, 0, what about this? What about this? This is easy too, but we don't know this. Like, let's say, what do you want it to be? Like, what is your suggestion? Let's start with 3. It can't be 3, right? Because if we say this is 3, you should have some way to make it 1. So it's not 3. So let's say it's 2. It's not 2. Because you have no way to make it 1, right? What is the definition of set of size 2? Its definition is you have two choices, to make it 1 or to make it 0. So this is not 2, this is not 3. Why? Because you can't make it 1. Just a flashback. We have two choices, yes. But let's say, what about this? Here, we have one choice. But actually, we don't have any choice, right? It's lose. Like it's a lose state. We will lose here. So sets used to be very easy, like counting number of options at the beginning. But when we are going into more advanced games, they are not number of options we have. Some options are fake, like this one, which you will go with this option to hell. Like it's no option. Like there is an option, but there is no option. Like you are forced to lose, so it's not an option. So let's redefine set of tokens, not to be number of options, but to be, so we want to find a Grundy number that using that number, you can go to all of the numbers less than it. So you should have option to go to 0, to 1, to 2, to 3, and to x minus 1. Let's say g minus 1. Let's make a flashback to where I was proving how we can win. Do you remember? I said that we pick some y, and because we are able to make any number less than y, let's name y prime out of y. Like I can decrease y to anything less than it, let's say y prime. I can make that x that comes from XORing all of the elements but y. Do you remember that? That's why when I say Grundy number of this vertex is, for example, 3, I should be able to convert it into 2, 1, 0. If I can't, the proof fails. Okay? So here it doesn't working with number of options and all. It's working with what other numbers I can convert y into, And we suppose that I can convert it into any number less than 1. So given that Grundy number of this vertex is just 1. Given that, let's come back to here. It was 0, it was 1, this is 1, 2. What is the Grundy number of this vertex? Yeah, why? Yeah, mix of them. I can convert it into 0 and then 1. So we heard a new word, which is mix. Yes. So mix comes in and helps us in like solving game theory problems, as I will tell you. So usually in game theory problems, what we have is this. Either we have some games to play parallelly. So consider we have a lot of games, like n games, and they are being played together. Like they can be even unrelated, like some sets of tokens and some trees to be played. To calculate the Grundy number of the entire game and then to find who will win. So let me know. When Grundy number is 0, what happens? It's lose. Because we don't have any option, we lose. And when Grundy number is something less than 0, something greater than 0, we will win. Now, consider we have a lot of games like this, and they can be different games. But we calculated Grundy number for each of them. Let's say G1, G2, G3, G4. Now, consider that we are playing these games in parallel, all of them. What is the Grundy number of this new game? No, it's not mix. XOR, yes. Why? Look, what was NIM? You remember? NIM was playing on different sets of tokens in parallel. And what we did? XORing them. Now consider another case. It's a game that you can choose out of G1, G2, G3, G4 what game to play. Then what is the Grundy number of this game? No. So again, there are 4 games. I have Grundy number of each of them. Now, mix of them. Yes, I have choice. Consider I have choice, like as the first player, which game to play. So what is Grundy number of this game now? Mix of them. So whenever we have some games in parallel, what do? Yeah. And when we have some choices, what do? Yeah. So so going on, we will just see where the games are parallel, where we should choose one option, and that's it. Like it will solve all of the game theory problems you'll see.